Okay, so this is just the basic. Yeah, I'm sure all of you know this now. So if you have a comparator, you have to know that this is, you can have a plus or a minus. So make sure you don't be careless of the signs. And anytime you have a signal or whatever variable that comes into the block, then what comes out is multiplied by the transfer function. Okay, and this is called a pick-off point. So if you have a pick-off point like this, whatever that goes to, it's the same thing will go to the two pick-off after the pick-off points. So this is still C, this is still C. Yeah, what you see here, this is still C, this is also still C. Okay, so this is not C, sorry, right? It should be D ke apa ke? D1, D2 ke? Yeah. Now, you have seen the standard feedback control closed loop block diagram. So, now this is what you saw. If you have a block diagram, it can be, okay, there can be variations. You can have the disturbance coming after the process. This is more common actually, or you can have it coming. This is after the process. You can have it coming before the process. Okay. Now this is GD star, because this GD star, yeah, GD star is not the same as GD. If this is for the same feedback closed loop system, GD star, yeah, GD star will have to be GD divided by GP. Yeah. Okay. So GD star is GD divided by GP. Because whatever comes out here, you have D times GD star, and then the GD star will be multiplied by GP. Okay, so if you have GD star is GD over GP, then the GP will cancel out. Okay, so you have to be careful. Now, sometimes you can see certain diagrams where there's no transfer function here. You have D going straight like this. Yeah. Now this is very convenient, because this is very convenient when you have the disturbance has the same transfer functions as the process. Okay, so you will have Y is equals to GP times U plus GP times D. Okay. Yeah. So sometimes when the disturbance has the same transfer function as the process, so this is a more convenient way of drawing it. But usually this is the normal way. This figure 11.8 is more normally seen. Now, like Anas was saying, what if we have another disturbance? So then you just add another comparator and you can have another one here. And remember, don't make this silly error. The feedback has to come out from a pick-off point. Do not put the feedback line here at the comparator. This is wrong. You will get at least 5 points taken off if you do that. Yeah, it has to be coming out from the pick-off point, because this is Y, this is also Y. Okay. Are you okay? Faham tak?
Faham betul.
Faham tak ke?
Okay, so this is basically the derivation. I think all of you have managed to follow it. Now there was a question on block diagram reduction. So let's say you have this block diagram reduction mainly means that you combine the block diagrams together. So instead of having G1, G2, G3, you can just put a border here. So when you want to have X3 over U, it's just G1, G2, G3, this is X3 is U times G1, G2, G3. Okay, so this is it. So that means these three block diagrams have been combined together, collapsed into one block diagram. So now the blocks become like this at the bottom. Okay, that's basically the meaning of block diagram reduction. Okay, boleh tak? Okay, so I can assume that you understand lah, tak ada apa. So this is the transfer function. Now, we don't have time to do this. Can you please take a picture of this and give me the answer nanti? What is y is equals to what? Y over m bar. Give me y over m bar. Okay. So you have these two disturbances coming in after GP and you have these two disturbances coming before GP. Okay, so get the transfer function y bar over m bar. So the concept of transfer function is still the same. It's still output over input. So if I want y bar over m bar, that means there's a block around here. I'm blocking this one. Okay. Now, if you want, in some cases, you may have certain things like this. You will see later on when we do feed forward control and everything, the block diagram will be, there will be additions to the block diagram. So let's say you have this in the middle of the block diagram. So instead, after the controller, instead of having a simple valve, you have something that has this. Yeah. So you can actually derive it. Yeah. So if you want to know, let's say this is y1, right? Y1 is equals to G2. Now, y1 is equals to whatever that is coming out of G2. But let's say this is y2. So y2 would be whatever is coming in here and whatever is coming in. This is plus and then this is minus. Okay, so this is sort of a feedback also. So you can derive it such that you have, you know what is y2 times g2. So to get y2, then so this is this plus this minus this. Okay. Okay, so you can basically if you derive it, then you'll get G8. Yeah. G8 is the transfer function from here to here is G2 over 1 plus G2, G6, G7. Yeah. And so you can collapse this and represent this as just G8. Okay. So it makes it look simpler. So this is just simplifying the block diagram or whatever some people call it, block diagram reduction. So CS3A, basically this is what you will have. Betul tak? Yeah. Now, many of you correctly pointed out that there'll be two block diagrams, one for level and one for the temperature. So to have the disturbances in the block diagram. Now, I have about 10 more minutes to explain about feedback controllers. Now, you have all explained quite well in the videos. We can put up the videos on YouTube and make it unlisted. So that, but if you want to make it listed, you can tell us, we can make it listed so that everybody else can also listen to it. But we will put up the videos and make it unlisted and give you the URL in the class e-learning so that all of you can listen to the recording again. So feedback controllers, this is just for your information. I want to introduce you to on-off control because this is very, very common. If you have things like a final control element like a solenoid valve, solenoid valve is just open or close. You cannot adjust the valve opening. Yeah. So it's called bang bang or two position control because it's either on or off or it's either open or close. Yeah, because it's very simple and it's the least expensive. Okay. Now, but then you have to have a process with a large capacitance for this to work effectively or to be acceptable. Let's say you have a thermostat for air conditioning in a building. Yeah, air condition compressor is either on or off. Yeah, so you don't have either the compressor is on or the compressor is off. So either your air conditioning is blowing in the cold air or it is stopped. Okay, that is also on-off control. Now, but sometimes you need to have continuous control. Now, this is a two-position control. This is called gap action control. There's a slight difference because this one depends on a range. Yeah, there's a lower boundary, that's an upper boundary. With the two-position control, you just have a set point, and then it will be on either on or off, open or close, open or close. Okay. In this case, for the two-position control or the gap action control, sorry, not two-position control, the gap action control, it depends when you hit the gap. Yeah. So very much depends on what we want to get. So this is a typical response of the feedback control. I'm sure you have seen this in the book. Yeah. When you have no control, by the way, when you look at the graph here, okay, this is obviously the control variable y. Let's say this is y. Is this regulatory control, like regulator control, or is this servo control? Can anybody tell me?
Servo.
Now, for you to know whether it's servo or regulator, I want to give you a clue. Where is the set point? Where is the set point? Can you see where the
Why, Prof?
Y is a control variable, okay? Tapi the set point dekat mana? Where is the set point? Is it somewhere above here?
Prof. Prof.
Yes.
The graph, the area under the graph.
Area. Because a set point has to be a value, cannot be the area.
Is it 0, Doctor?
That's a 0. Because you have to understand, when we are plotting this is in deviation form. Okay, so this is the initial value. This initial value is actually the set point. Yeah. So if the set point is here, is it a regulator problem or a servo problem?
Regulator.
Okay, regulator problem is when you want to keep the control variable at the set point, right? Despite having disturbances coming in. Correct? Yes? Betul tak?
Betul.
If you want the servo problem is you are changing set point and you want the control variable to follow and go to the new set point. Correct?
Yes, correct.
Yeah. Okay. So if you look at this diagram, do you think it's a problem where we want to bring the set point, the control variable to a new set point, or you want to keep the control variable at the current set point?
New set point.
Current set point.
New, okay, new set point or current set point?
Current set point.
Okay. So you can see that obviously there's disturbances coming in, and you want the control variable to stay at that set point, right? Because there's disturbance coming in, yeah, without any control, the control variable will go up like this. Nampak tak? Yeah. If you're using proportional control, then proportional controller is notorious for the offset. Depending on the KC, you'll still get offset. So this is why proportional control is up here. So there's disturbance. Now the disturbance have managed to upset, cause some offset in the system. Control variable is not at the set point anymore. Now, for PI, anytime you have integral control, it will manage to bring back the control variable at the set point. Yeah, finally there will be no offset, but it will cause this oscillatory response. Okay, now derivative action, because of the derivative part, then because there's a derivative of d, dt. Yeah. So when you take a derivative of the error, that means you know how the error is changing with time. Right? So this DEDT term provide information how the error is changing with time. So that is why sometimes the derivative mode is called as anticipatory control, because it can anticipate the error. Now, when the error is getting bigger, then DEDT will be greater than 0. Betul tak? Yeah, the derivative value will be greater than 0. So with a positive DEDT, it will contribute to cause the controller signal to become bigger. However, if kita ada ni okay. If the error is getting smaller, yeah, the derivative will be less than 0. So when the derivative DEDT is less than 0, it will cause the controller signal to be slightly smaller, yeah, because now the error is getting smaller. So it is helping the controller signal to adjust to whether the error is getting bigger or getting smaller. Okay, so that's why when you have the derivative, when you add the derivative mode, it helps make the process more stable. Yeah, it will lessen the oscillation. It will settle down quicker. But the integral part is very good in eliminating offset. However, it will keep growing and growing and growing because it's the area underneath the curve. Yeah. So because it keeps growing, it takes time for the value to go down. That is why you have this oscillation. Okay. So that's the effect of using the integral and the derivatives. Yeah, when you are integrating the error or when you're taking a derivative of the error. Okay. So you have described this just now. You have described proportional band and so on. Basically, KC, the bigger the KC is, the more sensitive the controller will be. And it is very fast and very easy because there's only one value to adjust. However, you will have offsets if you just use proportional control. But for some types of systems, you do want to have the offset. Yeah. So there are times when we do use only proportional control. For PI, when you add the integral part, then the integral will help us eliminate the offset. But because we keep on adding on to the, it will keep adding on to the value because of the integral of the error, then you can have reset wind up or integral wind up. Yeah? That means the controller continue to take action even though the control variable has already reached the set point. That's why you see the oscillation. Okay. So, okay. So the derivative part, this is what I was saying. Alamak, it ran away lah, the code 0 to t ni. You have dE dt. When you have dE dt, it becomes anticipatory control. Alamak. Okay. So, however, when you use the derivative part, usually integral only or derivative only control cannot be used, unlike the proportional only. Okay, because integral only will take time for the integral to build up, so there will be no action. The derivative controller, if you only use the derivative part, it will only take action when there's change in the error. If the error is constant, then no action will be taken. Okay, because of the derivative part. That's why normally integral only controller is not used, derivative only controller is not used. And because the derivative part depends on the change in error, if you have anything with noisy signal, then it's not suitable, because then the controller signal, the error will keep on changing. So there's of course advantages and disadvantages of feedback control. You can take immediate corrective action whenever there's error, but then it has to wait for the error to occur, then only then you can take action. A process model is not required, very easy, you just tune the 3 parameters of the controller. So it's very versatile, very robust, you can use it for almost all the processes. Yeah. There is of course disadvantages. If with feedback control, the error has already happened. That means the disturbance or the change has already taken place in the process. Only then do you take corrective action. Okay, and there's no predictive control action. Of course, you can anticipate it with the derivative part, but still it's not enough. You will still get the error going into the system. If you have a process with large time delay or dead time, then it's also problematic because it will take time. The error would have been in the system for quite some time before the controller realizes it. And when the control variable cannot be measured, then feedback control is not possible. Okay.